Hello, and welcome to 30 Mechanical Minutes, the free webinar series delivering virtual content for real-time professionals. My name is Doug Picklick, editor of HPAC Magazine, the leading publication and resource for mechanical contracting businesses across Canada. This episode is being sponsored by RLS, the makers of the patented rapid locking system of flame-free press fittings for HVAC and refrigeration industries. The topic of today's 30 Mechanical Minutes is a refrigerant update. We'll be looking at some of the conversion considerations from refrigerant phase downs in the past and where refrigerant phase downs are headed in the near future. I'm joined today by two refrigeration industry experts who will be sharing their experience and knowledge on these topics. First, Dave Demma is a regular contributor to HPAC Magazine, providing informative and insightful refrigeration articles for our readers. For his day job, Dave is a national accounts manager with United Refrigeration. He holds a degree in refrigeration engineering and worked as a journeyman technician before moving into the manufacturing sector, where he regularly trains contractor and engineering groups. Jeff Zimmerman is a district sales manager with Emerson Commercial and Residential Solutions. Jeff has 27 years of experience in the refrigeration industry and also serves as chair of the HRAI Refrigerant Landscape Task Team. Dave and Jeff will lead the discussion today and speak for about 30 minutes, and then we'll open the floor for a few questions. So feel free to type your questions into the questions tab on your control panel, and we'll try to get to them all. This webinar is being recorded, so you will be able to review anything you miss. Without any further ado, I'm going to hand this off to Jeff to get things rolling.
Okay, so thanks for the opportunity today. I think it makes sense to discuss the past before we discuss the future. So you've got three steps on this slide. The first is talking about the thinning ozone layer. Back in 1987, the Montreal Protocol was signed by 197 countries. At the time, the thinning ozone layer, part of the properties that were attributed to the thinning ozone layer were the refrigerants that we were using. They were CFCs and HCFCs, and so we needed to move away from these refrigerants. So at the time, the Montreal Protocol on substances that deplete the ozone layer was signed. It effectively banned HFCs and HCFCs through a phase down approach. And we were transitioning to non-ozone depleting refrigerants. So today, here we are, global warming is an issue, greenhouse gas emissions. And so today's refrigerants are attributing to global warming potential, and we're now looking at moving to either natural or low global warming potential refrigerants. So I'll talk about this on an upcoming slide that talks about the Kigali Amendment and the shift to these refrigerants.
Okay. Dave?
So the portion I'm going to be dealing with has specifically to do with what refrigerant to choose when you're faced with doing a refrigerant conversion. And that may be moving away from 22 or 404A or 507 or other refrigerants that are considered to be less desirable these days. And there really are several things to consider. And I guess I'll state right here that there are no drop-in replacements for any refrigerant. Each refrigerant has its own specific thermodynamic properties, which then determine system capacity, things like oil requirements, etc., which are considerations when choosing replacement. Other things to consider too are the price and availability of the conversion refrigerant. Any relatively new refrigerant is going to be under patent, which means that it'll be only available at authorized distributors for that particular refrigerant. And typically any refrigerant under patent is going to be significantly more expensive than an out-of-patent refrigerant. The environmental impact is another option to consider, and depending on the end user, that may be number one on the list. Some high volume retailers seem to be very concerned with their, their environmental appearance, if you will. So there are some large grocery chains, for example, that may be the primary driver in what refrigerant they choose. Complexity of the conversion really is a result of the properties of the refrigerant that you're choosing, and if they're significantly different from the refrigerant that you're replacing, you may be faced with replacing control valves, possibly upsizing piping and things like that. Industry experience has determined that all neoprene seals need to be replaced, so we'll discuss that in a little more detail in a little bit here. And then finally, don't believe everything you read. And there's so much information available online, it really would behoove anybody considering a refrigerant conversion to do some research on your own and find out what, from experiences and, industry reports that are online to see what refrigerant would best fit your set of circumstances. So you can move on to the next slide, Doug. So this is a small list of R22 replacements, and the things that really to take a look at here are, number one, what is the capacity of the prospective replacement compared to R22? So, for example, not to pick on any particular refrigerant here, but R424A with a 28% drop in capacity compared to 22 probably wouldn't be the most ideal choice unless you have just lots of extra compressor capacity that you want to use, but that typically isn't the case. So that's one thing to consider. And the other thing to consider is the mass flow requirement compared to R22, because that's going to determine whether you're going to need to replace and upsize expansion valves, refrigerant distributors, and things like that. So, for example, go back to the previous slide. Oh. Not quite done yet.
Right.
So, for example, if you look at R421A, for example, it's actually got a little bit more capacity than R22 does, but it's got its mass flow rate is fairly close to what R22's is. And the same thing for 417A, very close, but there's a significant capacity drop there. So ideally, you would like to have a refrigerant where the capacity compared to 22 and the mass flow compared to 22 are pretty close to what it would be with R22. So there's several to pick here. 407A is a pretty good choice. 407F is a decent choice, although it's going to tend to have higher discharge temperatures than 407A, so that may be a downside, and so forth. So, and as you can see, 448A, which is a fairly new refrigerant, but being quite widely used because of its lower GWP, has got good capacity compared to 22, and the mass flow is fairly close too. So go ahead and jump to the next slide now. So this is just up here to show that there's not an unlimited supply of building blocks to make new refrigerants. All of those refrigerants on the previous page are made out of the same roughly 4 constituents: R32, R125, R134A, and R143A. And then some of them have a hydrocarbon component, like, for example, 438A. Those numbers are awful small, but let's see. It's got a small percentage of isobutane in it, and those hydrocarbon components are strictly there to allow the refrigerant to be used with mineral oil. And then the last couple on the right, and that's 448A and 449A, they're actually a blend of HFCs and HFOs. So there's 2 HFOs listed here, Y1234Z, if I'm reading those small numbers correctly, and Y1234F. And they're very similar in property to 134A, but they've got extremely low GWP values. So the HFC, HFO blends essentially a portion of the 134A has been replaced with these HFOs to bring the GWP total down. So next slide. Oil is a consideration, and the compressor manufacturers, and this dates back to the days of replacing 502 or R12 with respectively 404A or 507 or 134A, which those replacements require POE. And at that point, and this is going back, what, 15 years or something, maybe a little longer, but the compressor manufacturers are pretty much all in agreement that when replacing a refrigerant that requires mineral oil to one which requires POE, that multiple oil changes are required, and with the end result of the percentage of mineral oil being less than 5% of the total amount of oil in the system. So that is still the compressor manufacturer's recommendations, although we have seen a lot of field experience where ratios of POE to mineral oil are up in the 50% to 50% range without any issues. I have seen some customers using, like for example, an R22 package air conditioning system with very small piping runs, because it's a self-contained piece of equipment, where they leave the mineral oil in the system after a conversion to 407C and add a small amount of POE to the system without any negative impact. Now, the compressor manufacturers would not probably endorse that. And I'm not saying I endorse that, but I'm reporting what we've seen contractors do without any negative impact. So next slide. And this actually addresses that. Probably this is maybe 10, 12 years ago. One large supermarket chain was using 422D as a replacement for R22. And 422D is a refrigerant that does have a hydrocarbon component and can be used with mineral oil. But we found in some job sites that because of the long and complex piping runs that you see in a supermarket, that even though 422D was designed to be used with mineral oil, there were oil return issues. So Copeland came out with a bulletin essentially stating that if you've got, in this case, 422A or D, but really you could make the statement for any refrigerant containing a hydrocarbon component that is designed to be used with mineral oil, if you're having oil return problems, add a percentage of POE to that system. And I saw this on job sites where 5 to 10% of POE was added to the system, and it eliminated all the inability to return oil issues that were being experienced. So that goes back to this one contractor that has used 407C in small, like package units with small piping runs, left the mineral oil in and added a small amount of POE, as that Copeland bulletin addresses, and they have not seen any oil return issues at all with that. So, okay, this is on the bullet point of complex conversions. Control valves and control devices like refrigerant distributors or expansion valves, part of their capacity is based on the mass flow requirement for the given refrigerant. So if you've got using R22 as a baseline and a refrigerant distributor that's properly sized, and then attempt to use that on a refrigerant that requires a significantly more mass flow, it's going to be undersized. So go ahead to the next slide here. And the next slide. So this shows a system with a distributor nozzle on this particular R22 system. It looks like it's a 1.5 ton. Actually, it's a low temperature application, but the nozzle is a number 1 size. And so doing a conversion with 407A, 422D, 438A, 404A, or 507, and using the same refrigerant nozzle, we find that 422D and on to the right, all of those refrigerants, this nozzle would be undersized, creating too much pressure drop through that nozzle, which then would negatively affect the available pressure drop for an expansion valve. So I would say you don't need to remember numbers here, remember the principle. And the principle here is that on control devices, when you make a determination as to what refrigerant you want to convert to, take the existing control devices, like for example, this number 1 nozzle on this refrigerant distributor and see how it is sized with the refrigerant you want to use. And it may or may not be appropriately sized depending on the refrigerant you choose. So next slide. Well, let's skip this one too, and let's move on to the next slide. The same thing holds true for expansion valves. So their capacity is determined by the diameter of the port, the valve stroke, which means how far open that pin moves away from the port, and then the system conditions and the properties of the refrigerant. So all things being equal, the properties of the refrigerant are going to be the determining value here. So let's move to the next slide. And again, we've got the same system here, and it's a low temperature R22 1.5 ton system. And the thing about expansion valves on refrigeration systems, you have to look at their capacity in the wintertime and the summertime, because part of that capacity is based on the amount of pressure drop available across the valve port, which is affected by the head pressure. And then because the head pressure is determined in the summertime by whatever the high ambient temperature is, and then in the wintertime, we want to run that head pressure a little bit lower to try and increase our system capacity, because the lower the head pressure, the higher the compressor efficiency and capacity is going to be. So we want to take advantage of that in the wintertime. So we look at this particular valve that we've selected is a 2-ton valve, and at a ambient condition of, well, 115 degree condensing temperature, that valve is operating at 59% of capacity, which is fine. And then in the wintertime, when the ambient is lower and we're operating at a 70 degree saturated condensing temperature, it's operating at 99% of capacity. So that valve is selected fine. It works well in the summertime and in the wintertime. So if you take that same valve and use it for 407A, same thing. I mean, the percentages are almost identical to 22 because the mass flow requirement for 407A is very similar to R22. So if we take that same valve and use it on a 422D system, for example, it's got plenty of capacity in the summertime, but in the wintertime, it's severely undersized. You're asking that valve to do 49% more than it's capable of. So in this case, you would have to upsize that valve. And the same thing for 438A or 404A or 507. The existing R22 valve is too small to be used with those refrigerants. And in addition, one of the other things to look at here, the port size determines the valve capacity, and the power head on the valve determines what refrigerant the valve is to be used with. So even if the port size allowed you to use that valve with, for example, 404A or 507 and have enough capacity, it still requires a different power head than R22. So at least, you still would be faced with a power head change there. So a lot of information packed into a small segment of time there. But again, the basic thing to remember here is that if you're doing a conversion, or when you're doing a conversion, take a look at the existing expansion valve and see how its capacity fares with the new refrigerant. Okay, next slide. Okay, so this is actually that screenshot of a video that DuPont produced several years ago, and the seal on the left, I'll say it like this, the seal on the right is a brand new neoprene seal. The seal on the left is that same seal that's been soaked in R22 for 24 hours, so you can see it's significantly swelled. And this is one of the things that we found when conversions were first starting to be done, that people would experience refrigerant leaks after the conversion. And it had strictly to do with the fact that the seal swell rate changes depending on the refrigerant that it's being used in. And in fact, if that refrigerant has chlorine in it, it swells quite a bit more than it does on a refrigerant without chlorine. So essentially, if you're changing a system from R22 to, say, 448A, which does not have chlorine in it, that seal is going to shrink essentially because it's not going to swell as much in the presence of 448A as it does with R22. So the reduction in swell means that seal shrinks a little bit. So if you add that factor to what we'll see on the next slide here, is that an old seal has taken a set based on how it's, for lack of a better technical term, squeezed into the area that that seal belongs in the given valve that it's being used in. So it takes a set, and then it's old and it's hardened. It's lost its elasticity. So if you combine those two factors with the fact that this is going to effectively shrink a little bit, it becomes a bad seal after the conversion. So the industry recommendation is that any neoprene seal needs to be replaced during the conversion. Otherwise, you run the risk of seeing a refrigerant leak there. So next slide. One of the beauties of POE is that it has some very detergent-like characteristics, and that is, if you look at a little snippet of pipe down in the lower right-hand corner, that's and there's a little pile of stuff there. That's the final condition that oil decomposes into a powder. And if that's occurring in your system, and typically a low temperature R22 with high discharge temperatures would cause this, that stuff may be deposited all throughout the interior of the system, inside the pipe, in the compressor, in the condenser, in the tubes in the condenser, and so forth. And it may be lying dormant there, not causing any problems, but if you introduce POE into the system, it's going to bring all that stuff back into circulation, and it'll end up in the compressor crankcase. So it's really important to make sure that filter dryers are changed, suction filters are changed, oil filters are changed if they're being used, and to make sure that you look at the system a couple of days after the conversion and take a look at the oil in the crankcase and make sure that it doesn't look like that oil in the crankcase in this photo here. And if it does, then you need to clean the system up with filter dryers. Next slide. I had a customer a few years ago. They took on a new client, and they had an after-hours call, and the system was short of refrigerant. So they looked at the nameplate on the piece of equipment and saw that it contained R22. So after repairing the leak, they added some amount of R22 to that system. The next day, the owner asked them, "Why did you put R22 in that? We converted that system to 407A last year." Well, the technician that did the conversion forgot to label the equipment. So this might seem like a really, relatively unimportant step in a conversion here, but it could actually be quite costly for the contractor if the, system is not labeled correctly. So make sure to label the system after the conversion. And I think that may be my last slide, but let's move ahead. Oh, one more slide. This is where I say, do your homework and read the fine print. So this is a refrigerant, and again, I'm not going to name the particular refrigerant and incriminate anybody, but it's listed as a drop-in direct replacement for R22, both in air conditioning, low and high temperature, blah, blah, blah. But if you read the fine print in their literature, it says it has a higher volume flow rate, so it has a higher mass flow rate requirement than 22, which may require OEMs to increase appropriately the size of liquid lines to optimize performance. You may have to decrease the length of a cap tube or increase the diameter, or a combination of both, because of the higher mass flow, the existing cap tube, and I would say expansion valve as well, is going to be undersized. In fact, they covered that in the next bullet point. The recommendation is the expansion valve should be sized to accommodate 40% greater mass flow than R22. In addition, the bulb in this particular refrigerant requires an R502 thermostatic charge, which would be the same as an R404A charge. But the point here is that not only do you have to upsize the valve, the existing R22 power assembly is not going to work with this refrigerant. In bullet point 3, they again address the fact that the liquid line size may need to be increased. Let's see. To optimize system performance, evaporator and or condenser capacities may need to be altered in some cases. And then they talk about the oil issue. This is a refrigerant that has a hydrocarbon component and is designed to be used with mineral oil, but they state if you've got a long or complex piping, the replacement of up to 25% of the oil with a charge of POE is recommended. So, as I said earlier, there is no direct drop-in for any refrigerant because they're all different. They all have different requirements in terms of oil. They all have different mass flows and different, thermodynamic properties, etc. So the thought that you can take one refrigerant out, put the next refrigerant in, and simply walk away, that isn't possible. And that's the definition of a drop-in refrigerant replacement. But this particular one is anything but a drop-in. I mean, they list in their literature all these things that you may have to, change from the existing system, and it doesn't really jive with their main bullet point being a drop-in replacement. So, again, do your homework. There's tons of information online. There's tons of experience from people that have done conversions online, and don't trust the carnival barker to say that when he says his product is the best one in the world to take his word for him for it. So do your homework. And I think that's my last slide. So I'll turn this back on over to Jeff.
Right. Thanks, Dave. So the Kigali Amendment to the Montreal Protocol. This October 15th, 2016, we've had 65 countries that have ratified this agreement. The chart in the lower area on the left side is developed countries like Canada. We've ratified this agreement, and our first phase down step in 2019 was 10%. So next step down in 2024, we'll go down to 60% of the original value. On the right, we've got a developing country. These are countries that haven't yet moved to these new HFCs. So they needed time to move away from CFCs and HCFCs, and then their phase down will begin 2024 is sort of like where their baseline is established, and then they'll phase down from there. So next slide. So building on that same chart, we've got two new areas on the right. The lower right portion of the slide shows the Canadian phase down schedule by percentage and dates. So the Kigali Amendment sets forth a phase down schedule, and this mirrors that. So you can see there's a baseline number on the bottom right of 18 million. Now that's the units are in CO2, tons of CO2 equivalent. And the way that was determined was they took consumption between the years of 2011 and 2013, and then added 15% to that for growth. And then, okay, that establishes our baseline, and then we'll start phasing down starting 2019. And, the final phase down will be 2036. We'll be down to 85%. So, it's important to know that equipment that's been installed now or previously that uses these fluids, we will continue to have refrigerant available for those systems.
Jeff, I think we will both be retired by 2036, right?
Hoping so.
Okay.
What a great thought,
Sorry.
Dave. No, thank you. In the upper right portion of the slide, I guess I should say it's a two-phase approach here in Canada. So Environment Canada put these rules in place. They set, one, the objective of the phase down approach, but also two, specific bans by category of equipment. So we've got 1, 2, 3, 4, 5, 6, 7 different commercial applications listed here, and then a GWP limit for those refrigerants, which we will see some GWPs for refrigerants on the next slide, and then a date for the effectiveness. So, come January 1st of this year, 2020, centralized systems, these are racks, medium and low temperature, large systems that hold a lot of refrigerant in grocery stores are limited to 2200 GWP. And then you've got condensing units, also at 2200 GWP. And then we've got reach-in units. These are small, self-contained standalone units, maybe they contain ice cream or pop, point of sale type things. Low temperature limit is 1500 GWP, and medium temperature is 1400 GWP. So, we'll see on the next slide that these, we'll look at the refrigerants that they're phasing to, or we can see them now. I'll just finish off on the upper right section that chillers will be required to move to a refrigerant under 750 by 2025. So let's move over to the left side of the chart now. And this chart's broken up horizontally into 3 levels. So on the top, we've got R410A, or high pressure refrigerants, R410A like. And then in the center, we've got R404A, or medium pressure refrigerants. And then on the bottom, we've got low pressure refrigerants like 134A. And then you can notice that there's a color code to these refrigerants. So these refer to the HRAI refrigerant class. And so green is an A1 non-flammable fluid. We're used to working with those today. Also on the bottom of the chart is global warming potential. So on the bottom left is 0. And then on the right, you can see 2000. Way out on the right is R404A and 507. The global warming potential of those refrigerants is almost 4,000. So, if you compare back to the upper right list, 2200, any systems that are working with 404 or 507, or any new systems that get installed would need, after January 1st, 2020, would need to be with a refrigerant below 2200. So that puts the 404 and 507 out for new installations. Now we've got 4 yellow boxes here on this chart. One is legacy equipment. This is basically where we're at today. And then we've got 1, 2, and 3, and these are sort of the steps of for replacing these refrigerants. So in this box, we've got legacy box, we've got R410A. And if we move to the left here in box 2, there are no air conditioning refrigerants listed there. If we go to box 3, we can see it's kind of small for my eyes, but R32 and R452B and 454B. There's also R466. So some of these fluids are pink in color, which is an A2L, or mildly flammable. And so our industry needs to get ready. Our codes and standards and our building codes need to be updated. We need to understand how to work safely with these refrigerants as they come on. So, 2025 chillers will need to move from 410A. It could very well likely be a flammable fluid that we're going to use. So, we need to get ready for that. In the number 1 box, which is basically a 0 GWP, we've got CO2 at the top, and then we've got orange colored NH3, which is ammonia, and then we've got red, which is R290 or propane. So propane's an A3, more flammable than the A2s or A2Ls, and a higher flame propagation rate. So, we're looking at things like, does the refrigerant burn? Does it propagate a flame? If it does propagate a flame, how fast does that flame spread? These are the type of things we need to know. These are the properties we need to understand with these refrigerants to make, informed decisions for their replacement and mitigation of risk when it comes to, possible fire, I guess. So also we've got, if we look at the middle row here, we've got 404A. So, today we see, 407s being used commonly as well. Those will remain, as will to the left, but just below the 1500 GWP line, you can see there's 448 and 449. So Dave talked a little bit about those refrigerants. And then, the next step from there, which we're not really ready for right now, but is to the left, to more pink or flammable refrigerants. So that's sort of the direction that we'll go in future. So this step that we're taking now for the Kigali Amendment, this is really just the an interim change. There will be more changes to come. And then, 134A in the bottom there in the legacy box, that's we've got some A1 fluids to replace that with as well. And, a couple of those are R450 and R513. So, okay, we can go to the next slide. Right, so HRAI's Future of Refrigerants task team developed this leaflet here to draw attention to the flammability aspect of some of the low GWP alternative refrigerants. It was sent out to industry and displayed. It's displayed on the refrigerant landscape page on HRAI's website. See the address there at the top. The leaflet provides details on key elements of the phase down. It informs of the refrigerant safety groups, the flammability aspect of some of the low GWP alternatives, the need for training, the goal of harmonized codes and standards across Canada. And the HRAI website also contains a list of refrigerants that you can click that and open it up, and it gives you chemical compound, the refrigerant class, the GWP number for that refrigerant, the ODP, some of the applications, and then some of the alternatives. So I guess there's a lot to take in here with these changes, and for more information, HRAI's website is helpful, or you give them a call.
Perfect. Actually, thank you so much, Jeff.
Welcome.
And Dave, we do have a few questions that have come in.
Sure.
So I'm going to start knocking these off. Dave, I think this one might be for you. Do neoprene seals require replacement? I think you answered this, but.
That would be a yes. And it's not my opinion. That really is the industry recommendation. There's a lot of track records, grocery stores, equipment manufacturers that all endorse, affirmative on the answer to that question.
Okay. Here's one. When will we know the GWP limit for residential air conditioning? Jeff, do we have any idea?
Well, actually, there hasn't been one set. If we go back to the original Montreal Protocol agreement, the idea was a phase down approach, and so there becomes this economic perspective that could be the driving force, where supply drops and price increases, and then it makes sense to look at these new refrigerants. It motivates end users to move there rather than legislating with a hard ban. So right now, there's no date.
Very good. Dave, maybe you can take this one. Can you talk about the ups and downs of R448A?
I don't know of any downs, really. It's proven to be a good replacement for not only 404A 507, but also R22. It's got fairly similar mass flow to R22. It's a little bit greater than R22, but less than 404A and 507. So in terms of expansion valves, it uses the same thermostatic charge that R22 would. So if you're doing a conversion from 22 to 448A, then you would use the existing expansion valves. If you're doing a 404A or 507 conversion to 448A, probably here you would have to just look at every expansion valve and see how its capacity would fare with 448A. There may be some cases where it may be too big, but even if the valve port size is correct for the tonnage you need, you'll have to change the power head to an R22 power head. So that might be considered a small negative. It does require POE. It's got a very low GWP compared to, it's about a third of what 404A or 507 is. So that's a positive. It's under patent, so it's a little more expensive, but we've seen that price come down some. So and honestly, there are a lot of people using this. I would say in the United States, most supermarkets are using 448A as their choice of refrigerant, just primarily for the environmental impact. and I have not heard of any negative, negative reports of anybody with 448A.
Okay. Jeff, maybe this one's for you. Why is it taking so long to get equipment meeting the correct AWEF ratings?
Well, this is a little off topic from today's
Right,
discussion,
okay.
but really the AWEF is, I did a review. I had a look at equipment manufacturers of refrigeration equipment recently, and what I'm seeing is there are AWEF values listed for equipment built today in both medium and low temperatures. So it may have taken a bit of time to get there, and they talk about max tech. What's the maximum technology that you can use to reach the highest efficiency? And so, we're kind of getting there. It's a bit challenging to reach these values, to find, to be able to build equipment and have them meet the AWEF values. So, using the most efficient products that you can get is a requirement. And I think maybe the first focus was on medium temperature, and then low temperature took effect in July. So I think we're there now. I think we're well positioned in the industry. I don't think it is an issue now.
Okay. Someone had asked, is 410A no longer applicable for chillers starting next year, 2021? I don't think that's what the chart said. Was it, Jeff?
No, it's 2025. 410A will continue to be here. Again, we've, in Canada, we've dropped imports by 10% starting 2019, and then we've got another 30% reduction down to 40% in 2024. So that'll continue. We'll be able to service the equipment that's installed now, and for new equipment, 2025 is the date.
Okay. Someone has asked, what are the precautions with using CO2 as a refrigerant? Either of you?
Well, CO2 is much higher pressure than what we're using today. It does have a GWP of 0. There is some aspects of the system you need to be able to keep the CO2 cooler in the event that there's a power failure and the system's off. That high pressure might vent to the outdoors. So there's just things to consider. And there may not be, like we've seen some grocery store applications move towards CO2, perhaps, to be green and environmentally friendly. So, there are some factors to consider. Anything to add, Dave? Or?
Maybe a couple of things. CO2 certainly isn't as readily available as our common refrigerants, so that's an aspect. If you're evacuating a system and then, charging it with CO2, if you don't first charge that evacuated system with vapor and bring it up to a certain pressure, if you just, like you would with a normal refrigerant, dump liquid into a system, that liquid then turns into dry ice inside the pipes, and that becomes a little problematic to have to wait for that to melt so you can, properly charge the system. So that's something we're not used to seeing, a liquid turning directly into a solid at a low pressure. Also, along the lines of Jeff mentioned the high pressure, and you see this with ammonia too. If you've got like a hand valve and a control valve that could become closed, like during a power failure or something like that. I mean, the hand valve certainly could be closed by manually closing it, but then a solenoid valve or something. And if you have some liquid trapped between two closed valves and that temperature increases, it could easily increase enough to burst some pipe or something like that. So CO2 systems are installed with a lot of bypass check valves to eliminate that kind of thing, but if those are not correctly installed, you could have a little problem in the case of a power failure and trap liquid in a system building up to a very high pressure. Okay. And then the technician training, I think, is an issue too. I mean, being an unknown refrigerant in a very different kind of system, there's a learning curve there.
Okay. Dave, I think this one's for you. It's under factors consider, point number 2. That was in your presentation. Is the need to potentially increase system capacity being considered when comparing AWEF values, saying more power draw equals more stress on the grid?
Well, I guess number one, I would say a refrigerant conversion, at least in the States, I believe, I'm not sure about Canada, but that existing system in just converting refrigerants would not be affected by AWIF regulations. And number two, if you've got a 2-ton system, regardless of what the regulations are, you're still going to need 2 tons afterwards. So I don't know that AWIF really applies to that, but again, it's important to make sure that the refrigerant you choose can provide sufficient capacity for what's required in that system.
Right. Jeff, here's a question I'm not sure you can answer, but when will Canada allow R32 in central piped AC and heat pump systems for residential and commercial installations?
Well, yeah, I don't know that I have an answer to this. Building codes need to be updated. You know, they've got a 5-year code cycle generally. The codes that like HRAI 34 has been updated, and B52, the mechanical refrigeration code, now is updated to reference the most current version that includes A2L refrigerants. But we really need to get to the point where we understand how to safely work with these fluids, and if you've got a high charge potential for leak inside the building, do we need a way of mitigating that risk? Maybe a refrigerant sensor, or in a ventilation fan or something like that. So I don't have a specific answer as to when the codes will be ready. I mean, we know we kind of need to be ready by 2025, don't we? So I would say between then and now, we'll have some work to do.
Right. Well, this next question kind of leads into that. Will future refrigerant alternatives ultimately have to include fire protection or prevention measures in AC refrigerant, air conditioning and refrigerant equipment?
Will the equipment house the risk mitigation, or will the building? It's hard to say. I think more towards the building and less towards the equipment, but I would say that's absolutely a factor, and there's been a phenomenal amount of research that's been done. There's on HRAI's webpage, there is some testing that's been done, and they're looking at different lower LFL and HFL, lower flammability limits and higher flammability limits of refrigerants. And if there is a leak potential, say in a residence with maybe a standing pilot water heater, what is the likelihood that refrigerant, which is heavier than air, travels down to the floor and it's within its flammable limits, and then the pilot light lights it? Like, that kind of information is out there, and you can be assured that technical committees will be reviewing this information to make sure that whatever the code looks like, we will be safe.
Right. Dave, this might be for you. Does a Teflon seal in a Rotolock valve need to be replaced?
No, Teflon seals do not need to be replaced, nor do the typical, paper type gaskets, or like head gaskets that are rubberized metal. They do not. And I guess I'll add to that Sporlan, probably around 2000, I believe, they changed their solenoid valve seals from a neoprene. It wasn't an O-ring, it was a excuse me, quadra seal, which was kind of like a square O-ring, but they changed from that material to a Wolverine gasket, which is basically a rubberized metal gasket. So neoprene is the only seal that really needs to be addressed during the conversion. All others are fine. Okay.
And this is the final question we've got. And the person is asking, if we put in an R410A mini split today, what could we refill it with in 5 or 10 years from now? Jeff?
Well, the equipment's approved for 410A, and we're not we're not going to, our 410A is not going anywhere. It'll still be available. So I think the right choice is 410A. Yeah.
Let me just add to that. I think this is probably, I probably get asked 1 or 2 times a month, so when is 410A going to be phased out? And certainly United States and Canada have different regulations, but in our country there has never been any talk about phasing out 410A. So I think this kind of lends itself to the point that there is a lot of misinformation out there. And this is one of those about, you know, when is refrigerant ABC going to be phased out? Well, we haven't talked about phasing that out. We may limit its use in new equipment, but outside of 22, there's nothing on the chopping block here anytime soon for being phased out.
Yep.
All right. Very
Totally
good.
agree.
Thank you, Dave, and thank you, Jeff. This was great.
Pleasure.
Thanks again for sharing your information, both of you. I know everyone watching has enjoyed what you've had to say. So with that, I'm going to put an end. So thanks again, Dave and Jeff, and thanks to everyone who participated today, asked a few questions, and thanks again to RLS for sponsoring this 2021 refrigerant update. That's 30 mechanical minutes for this time. Thanks, and we'll see you at the next one.
Thank you.
Take care. Thanks.